Good afternoon, everyone, and welcome to this Norwich Science Festival at Home event. We're just waiting a couple of moments for everyone to join us and we'll get started. Are you making... Hello, everyone. Welcome to Norwich Science Festival at Home. I'm Natalie Bailey, Science Festival producer, and here is Mark Thompson, astronomer. Hello, Mark.
Hi, with a massive hand. Look at the size of that.
I know.
Oh my goodness.
This is all very new to us, this live streaming for the Science Festival, but thank you so much for joining us all, and huge thanks to our wonderful patron Mark for joining us too. This is the first live event of the Science Festival, so we have everything crossed for a smooth event. Just remember, while we're doing the event now, you can join in on the live chat on YouTube. So you can, if you've logged into your YouTube account, you'll be able to comment and ask Mark questions. He's going to answer as many as he can throughout the event, and he will also be on the live chat for a little while when the event ends to answer any more questions. For those of you young people out there who are watching this and who are doing their Youth STEM Awards, Mark, who is also a patron for Youth STEM Awards, he's very busy, you can also use watching this to count towards your award, so please do log your activity. So thank you again for joining us, and I'm going to hand over to Mark, who is going to thrill you with astronomy for the next half an hour or so. Over to you, Mark. Thank you.
Thank you, Natalie. Good afternoon, everyone. Well, so looking at the title on the screen now, The Night Sky Live with Mark Thompson, there's a slight change to the schedule for this afternoon. Let me just share my screen, if I can find the right button, and show you, because the plan for this afternoon is for controlling a telescope on the other side of the world, which sounds an incredibly exciting thing to do. But let me just share my screen. Hopefully you can now see my screen, and it shows the interface with which I would ordinarily control the telescope in Australia. However, as you can see, if you look over on the left-hand side of the screen, what we're seeing is cloud. So whilst I was hoping that we'd get some level of certainty for clear skies over in Australia, which is typically the altitude to the telescope, the Las Canberras Observatory in Siding Springs in New South Wales is at about 1,100 metres. Normally they get good clear skies. Today, typical for a live event, the first live event for the Science Festival, it's cloudy, which is the bane of my life. But still, we can still have a good experience, and I'm still going to talk to you about lots of things and talk you through how at least we can take images through telescopes. What I am trying to do is I'm rapidly trying to arrange for an alternative date when we can try another attempt at controlling a telescope if the weather plays ball. And, you know, it might clear up. So do stay tuned, and we might find that things miraculously clear up. What you can see on the left is the current sky condition. And as you can see, it's just a big, horrible, grey, fuzzy blob. Now, the great thing about using these observatories in other parts of the world, especially if they've got some kind of computer interface or web-based interface for them, is that quite often you can get these wonderful statistics that show you the weather conditions at that location. So we're now looking at the screen for the Siding Springs Observatory over in Australia, and it shows the air temperature, the pressure, the dew point, humidity, all that sort of stuff. Shows us pretty much everything that we as astronomers need to know to be able to control telescopes and to understand what the conditions are like. But as you can see on the left-hand side, all these other venues, we've got Sutherland, Teesside over in Spain, Cheratololo. I'm clearly not a very good linguist, that's why I stick to astronomy. The USA, Santa Barbara. There's a lot of cloud around the world at the moment. So, you know, we're not alone by struggling, and we've got cloud here in Norfolk as well. So unfortunately, we're not going to be able to control anything yet. If it clears up, of course, we'll hop straight across. But what I thought I'd do instead is we can still learn and see what kind of stuff we as astronomers do to take pictures. Of course, you guys, when you take pictures with your camera and your phone, you just pick your phone up and click away and you take a picture, and it's really easy. But astronomical imaging is a very different experience entirely. Now, let me just show you. I think have I shared an app, or I've just shared an app, I think. Let me just reshare my screen so that I share the whole screen rather than just the application. Right, let's share my desktop. Here we go. So what I'm going to show you is I've got some slides prepared just to give you a bit of a feel for the kind of things we're doing. Now, there's the location of the Siding Spring Observatory over in Australia, in the southeast part of Australia, latitude of 31 degrees south and a longitude of 149 degrees east. The longitude is not so critical to determine what we can see, but especially the latitude is really important, because here in the northern hemisphere, certainly in Norfolk or UK, we're about 52 degrees north, and so consequently we see everything, if you like, above the Earth. So I can demonstrate with my very expensive demonstration model here of the Earth, which is actually my dog's ball that she plays with. If this was the Earth, then of course we've got the northern hemisphere top half, southern hemisphere bottom half, and if we live here at the UK about 52 degrees north, then we can see stuff in that direction. What we can't see is anything down there because the Earth is in the way. So by having control of a telescope in the southern hemisphere, that enables us to look at a completely different part of the sky, which is wonderful to allow us to explore different objects. So using the telescope over in Australia is a great opportunity. The observatory itself is at 1,116 meters above sea level. Now, as you're probably aware, certainly where I live in Norfolk, it's quite a flat country, and you're lucky to get about 20 meters above sea level. But quite often, if you're about 1,000 meters above sea level, a lot of cloud that affects what we can see from the lower levels actually is below you. And so astronomers build these observatories on top of tall mountains or high ground, simply so that we can get above as much of the cloud as possible. Now, there's another benefit to having an observatory high up, high altitude, in that we get above the disturbance of the atmosphere as well. Now, I'm sure you've all noticed the sort of the shimmer and the haze that you quite often see, especially if you're looking along the surface of a road on a hot day, and that shimmer is the movement of the atmosphere. And we get affected by that as astronomers. We try and look through the movement of the atmosphere, and that can affect what we can see with, by making things less clear for us and less sharp. So again, by putting telescopes nice and high, then that means we don't have any issues, or we have less issues with that. So we tend to put observatories nice and high as we can, to try and get us away from a lot of the atmospheric issues that we experience. Now, so this is a picture of the Las Cambras Observatory over in New South Wales. The telescope we were going to be using is inside this called a clamshell observatory. So those funny looking segments that you can see on the screen there, they kind of open up like a clamshell would, and there's actually 3 telescopes inside that observatory, and they're all controlled across the internet. So whilst there are people will be based at the observatory for generally just for engineers and to fix and repair the telescopes and upgrade them sometimes. astronomers don't really often sit and look through a telescope anymore. So we normally just connect up to a telescope across the internet and control it from home, which, it's great. And so this was a telescope we were going to be connecting and controlling. It's a 0.4 meter. Actually, it's bigger than it looks in this picture. It's a 0.4 meter diameter telescope. It's a Meade Ritchie-Crichton telescope, and it's mounted in this sort of, it's actually a horseshoe shaped mount, and that allows us to move the telescope around to any part of the sky. We've got one axis of rotation just there, which moves the telescope thus, kind of moves it in uppy downy motion, if you like. And then we've got another axis down here, which is at that angle as you look at it, and it kind of spins the telescope around. And what you'll notice is that the angle of this axis compared to the horizontal, so we're kind of talking about that angle there, is equal to the latitude of where the telescope is based. And what that basically means is that it aligns this axis with the axis of the Earth's rotation. So as you'll probably know, if you look at the night sky, things rise in the east and they set in the west. And if we try and take a photograph of objects in the night sky, then we struggle because they move, and our exposures are not just fractions of a second like we get in normal photography daytime, but actually we can use exposures that are many minutes and sometimes even hours. So we need to somehow freeze the rotation of the Earth, and we do that by attaching motors to these axes of rotation, and effectively it's this axis which is pointing in exactly the same direction as the Earth's axis. And what we simply do is we turn it in the opposite direction, but at the same speed. So the telescope is very slowly moving with relation to the Earth, but not relation to the sky. So what happens is that it keeps pointing at objects as the Earth turns. So it's a bit like you see figure skaters as they spin, they keep fixated on a point to stop them getting dizzy. But a telescope gets fixed on a point in the sky, the object you're trying to photograph, and it keeps pointing at it until it either sets and you can't see it anymore, or of course you've finished your exposure. So so these are the kind of mechanics that we use. Attached to the telescope is a camera. It's an SBIG STL6303, a name that rolls off the tongue quite nicely. But it's a digital camera, a CCD camera, and what it does is it gives us a digital equivalent to film. And film is the thing that certainly older people remember from the days when you took photographs, you had to put film in your camera, and it was a fiddly job. We don't do that anymore. We use digital CCD chips, and they're electronic devices. And I'll talk about that in a few moments. But what we do if we want to take pictures, and of course some of you who follow me on Twitter will have seen that I put out a tweet earlier today that asked what you wanted me to photograph through this very telescope. And the options were the Tarantula Nebula. I'll show you pictures of these in a short while, but the Tarantula Nebula was one option, the Sculptor Galaxy, or the 47 Tucanae globular cluster. So there's three choices. The results came in and they showed that the Tarantula Nebula was top. So we were going to go for a picture of the Tarantula Nebula first. That was our plan. And if we had time, we'd have gone for a picture of the Sculptor Galaxy and then 47 Tucanae as well. So that was the plan anyway. Now, if we want to take pictures through astronomical telescopes, I'm just going to show you this. I'm going to flick up and down these slides because the whole afternoon's gone to pot now, but it's fine. We can deal with that. So inside a camera, a digital camera, inside your phone camera, inside a digital SLR, inside webcams, any digital camera, it has this thing called a chip, a CCD chip. There are modern versions of that called a CMOS device. But in this case, it's a CCD chip. And what it essentially is, you've all seen a solar panel, or maybe on a house nearby. And solar panels work by receiving light from the sun. And depending on how much light they receive from the sun, they produce a certain amount of electricity. Now, a CCD is a bit like a lot of solar panels all connected up onto a little device, generally only a few centimeters in diameter or in size, in a square shape. Some are maybe just a few millimeters, some are a few centimeters, more so centimeters these days. But this is sort of a schematic, a diagram of what a CCD chip might look like. And we'll focus on the one on the left-hand side for the moment. So if you look at all these little squares, these are called pixels, and each one of these pixels is the equivalent of a solar panel. So as this camera gets pointed at an object, then each of these tiny little pixels records a little bit of light, and depending on how much light there is, will determine how strong the electrical charge is that this pixel detects. So if it sees a lot of light, it will be a higher number. If it sees less light, it will be a lower number. And the more light that it receives, it will be white. The less light that it receives, it will be dark. And you can build up a picture by simply detecting the light over these tiny, tiny little pixels. Now, in reality, because they're a lot smaller than that. So this is how sort of a black and white, or rather a mono camera works. Now, your phone or your DSLR camera, it doesn't take black and white photographs. It actually takes color photographs. Now, to get a color photograph, what you have to do, and if you've looked at an old TV closely, you'll notice that if you look really, really closely at the screen, you'll see it's got loads of little dots that are red, green, and blue. And what we can do is we can use red, green, and blue to mix together to produce a true color representation of what you're seeing. And that's how you can get a full color display on a TV screen, by taking different amounts of red, different amounts of green, different amounts of blue, mixing them together. So, for example, if you had a high, strong red signal and a really low green signal and a really low blue signal, you'd see quite a strong red color. Similarly, if you saw a really strong green signal, low blue and low red, you'd get a really strong green color. So depending on what the color of the light is that this thing's picking up, we'll be able to reconstruct the image in true color by having a red, a green, and a blue pixel. But what that means is, for a black and white camera, which can pick up amounts of light in individual pixels, for an individual pixel's worth of image, then a CCD camera actually has to use a few more pixels. And that means that a color camera doesn't have what we call as high a resolution as a black and white or a mono camera, because it takes, so it's almost like you've got 4 of these pixels have to work together to produce the color image of what is a black and white or a mono picture. So what we need to do is astronomical pictures use typically will use a mono CCD chip. You can get color CCD chips these days, but you can't get mono CCD. Or, sorry, you get mono CCD chips normally in astronomical photography. You can get color ones, but these color cameras don't show as high a resolution. So these things will give you the ability to get a color photograph through a telescope. These won't, but the downside of that is that this is a much better resolution, which means you get to see a much higher level of detail than you would with this camera. So there's an offset. You either get really good color pictures, not as much quality of detail, or great level of detail, not as much color. So it's a bit of a balance act, and a bit of a kind of which one you're going to choose. So what we can do, though, is we can do something quite clever. And if I just flick back to the screen showing the interface, wherever that's gone, of the telescope system, what we can do in astronomical photography is we don't actually, and certainly the images I've taken, most high quality astronomical telescopes, they don't use color cameras. However, what we do see is we always see color pictures of astronomical objects. And let me show you. In fact, I've got a picture which I'll just explain how it works in a short while. There's a color picture of an object called M16, the Eagle Nebula, but it's taken with a black and white camera. And let me explain how that works. What we do, if I can find my others, this is where working with 2 monitors would work a whole lot easier. Now, this is the telescope or the camera interface, and the way this works simply is that you can type in the name of the object you want to photograph. So, for example, M16 or the Eagle Nebula, if I choose to take a photograph of that, then I'll type in its name, and that should automatically enable the right ascension, which is the location of the object in the sky, and the declination to be populated into these 2 fields. Now, just like every location on Earth has got latitude and longitude, which explains and describes where it is on the Earth, in the sky, we've got the sky's equivalent of longitude and latitude, which is called right ascension and declination. Right ascension is the equivalent of longitude, and declination is the equivalent of latitude. And by using these coordinate systems, we can point telescopes across the sky. Equally, if I didn't know the object's name, I could just type in the location. I could type in, let's say, 12 hours 23 minutes and 32 seconds. And that's a location in the sky in right ascension. No idea what's there in particular. It'd be useless if I didn't put in a declination as well. So I could put in there 01, let's say 10, 10, and that's the declination. There's going to be something in that location. Lord knows what it is. It's a completely random set of figures. But we can put the object's details in, or we can just pick from a list, which is really easy. So if we picked, let's say, M42, an object called the Orion Nebula, and you see it's already populated the right ascension and the declination on the screen. So we can do that to get the telescope pointing at objects in the sky. But then what we need to do is we need to get the color pictures. Now, as I said, we use black and white cameras to take color photographs in astronomy. It's a bit of a faff, but it works really well. It keeps the high resolution that a black or mono camera does, but it gets us the color pictures. And the way we do that is by using filters. And you can see on the screen now that we've got some filters which are red, green, and blue, just like the filter or the colors of the pixels on a color CCD camera or CCD chip. And we can say we'll have a red filter image, a green filter image, and a blue filter image. This will take 3 pictures of the same object. And we can say we'll have a 30-second exposure for red, we'll have a 30-second exposure for green, and a 30-second exposure for blue. And as you see at the bottom, it says this observation time will take about 149 seconds. And what the telescope will do in all that time is it will move the telescope across to the right position in the sky using the right ascension declination. It will normally focus itself, so it will take a picture of the field of stars that it comes across when it gets there, and it will find the stars, the brightest star in the image, and it will keep changing the focus. It will adjust the focus of the telescope until that star is as small as possible, which tells us it's as sharp as possible, and then it will start taking pictures. It will take a red image for 30 seconds, then it will stop, change filter to a green filter, take another picture, 30 seconds, stop, change the filter to blue, and take another picture of the blue through the blue filter. So it takes all this time to take all these 3 individual pictures. And what that shows us, or what that gives us, if we just flick back again to this screen, what it gives us, this is a run I did on the Eagle Nebula. That's how I got this color picture. It gets us a red image through the red filter. It gives us a green image through a green filter, and it gives a blue image through a blue filter. And that can be really useful because straight away what we can see is that there's an awful lot more data that is visible in the red than there is in the green and then there is in the blue, because the red, this is a very strong red colored object. It's actually an emission nebula, which gives off an awful lot of red light. So you'd expect, because it's very red in color, as you can see from the color image, it's going to show us a really strong red image through the red filter, not as much strength in the green, and even weaker through the blue. But then when you recombine all of those images through desktop processing software, it allows you to add the blue picture to the green one and the red one to the green and the blue. And then when you combine them all, you end up with something looking a little bit like that. But even the process of combining the color image takes time, because what you actually have to do is you have to run all sorts of different processes to make sure all the stars are perfectly aligned. Otherwise, what you'll end up with is a weird effect. And I can just kind of demonstrate that here. If I took the red image and the blue image and I change, this is in PowerPoint, so it's not even a real genuine experience, but if I change the sort of the opacity, so it kind of got a bit of a, you can see through the image, you'll see that as I move it around, you can see the background stars. And if I tried to stack the images one on top of the other when they weren't aligned perfectly, so at the moment you can see we're kind of seeing double vision through or of this object, then what's actually happening is I need to get the software to move the 2 images around until they're nicely aligned. So that one's almost, probably near enough, nicely aligned. And then you have to do the same thing with the other image as well, the blue image. And you have to align all the stars before you can then combine the colors, apply the filters to get the final true color image. Now, in reality, it's not as quick as that, because a 30-second exposure is quite a short period of time for most astronomical pictures. I'm just going to pop back and just see if the skies have, by any remote chance, cleared over at the observatory over in Australia. Let's just have a look, see if they have. Now look at that, still miserable weather. They're typical. So what we would ordinarily do is we wouldn't just take a 30-second picture, because actually the longer your exposure, the more light you gather, and the more light you gather, the more detail you get to see. So we can see an awful lot more detail if we take longer and longer exposures. And the more exposures we get, then, you know, the better quality pictures we see. So quite often you'll spend hours and hours and hours taking photographs, often running over many, many nights. And then you might then spend an equal number of hours messing around with the pictures in software to fine tune them and to make them look as good as they are. Now, it's not just red, green, and blue filters that we can use to see through or to get images of the night sky. There are other filters as well. So, for example, there's a hydrogen alpha filter. There's an O3, an oxygen filter, and there's a sulfur filter. So there are lots of different filters that we can use. And the beauty of the other rather strange titled hydrogen alpha filter sets is that those filters are called narrowband filters. And actually, if you've got a lot of light pollution in your area, then because they cut out so much extra light from the light pollution, you can still do quite a lot of astronomical imaging with those narrowband types of filters. But it does mean that because they cut out so much light, that the exposures have to be so much longer. And quite often, exposures of an object like this, the Eagle Nebula, could have to last for many, many hours, and it is really a labour of love. Now, I mentioned that the telescopes such as this kind of setup, and many amateurs across the country, the world, have got not necessarily this kit like this, but they've got, you know, scaled down versions of kit like this. Whilst you can set a motor going on this end of the telescope to follow objects across the sky, what you will find is that there's always going to be a level of mechanical error within the system. So whilst the telescope will be tracking, it will be following across the sky at a rate of the same rate of the Earth's rotation, but in the opposite direction, there'll still be moments when the gears aren't quite perfect enough, and there'll be moments when the tracking or the telescope doesn't follow it quite right. And if an object moves even just a little bit, or rather if the telescope moves just a little bit too fast or a little bit too slow, even for just a short moment, that can ruin an evening's work. So what we have is we have software, and what the software will do while the telescope is taking an image is it will be guiding. And what a piece of guiding software might do, let me get this bigger picture. A piece of guiding software, while the telescope is taking its image of the night sky, it will concentrate its attention on a star. And the software will just literally stare at that star constantly for the duration of the exposure. And if perchance the star starts to drift by even 1 pixel, then the telescope or the computer will say to the telescope, we've got a problem here, we need to go a bit faster because that star is drifting in the wrong direction, we need to slow down a little bit. And the telescope will constantly adjust itself throughout the entire exposure to make sure any mechanical errors within the drive system are resolved and taken out of the equation, so you get a nice sharp image. Back in the day when I started taking photographs of the night sky with film, you had to do that manually. You'd literally be stood peering down the eyepiece of a telescope, guiding the thing with buttons, trying to make sure that it didn't actually move. And it really was a labour of love. But thankfully, we've got computer software that will do that for us now, which takes the hard work out of it quite nicely. So we can take red and green, blue filters, and we can use those, we can recombine them in software, and we can do lots of other things as well in software. We can sharpen them, we can remove certain features, we can do all sorts of different things to enhance levels of detail, just to make sure that we get the best from the quality, not just from an aesthetic point of view, which, for certain occasions. So, for example, many of the Hubble Space Telescope images are enhanced for public enjoyment, and scientifically they're not necessarily a lot of use, but by adjusting them in a way that makes them look really pretty, that can actually engage with people an awful lot more. Whereas sometimes we also enhance things from a scientific point of view to enhance certain levels of detail. So there's a lot of work that goes in. Capturing the image is just the first part of the job. Once you've captured all the data, you've then got to go through the process of processing it, which does take as much time as well. So it is a labour of love. There are lots and lots of bits of software out there. If anyone is interested in getting into astronomical photography, there are lots of different ways you can get into it. You can certainly start getting into it through using a DSLR camera on a tripod pointing at the night sky, or you can even use smartphones. There are great apps out there that allow you to use smartphones to try and get some decent images of the night sky as well. So it is worthwhile, if you want to get involved in astronomical photography, you can do kind of the wide field pictures of constellations with just a camera and a phone. You can get satellite images. Getting pictures of the moon and planets, you really need to start thinking about a telescope, even a basic telescope. And you can quite often just use your phone, pointing it through the eyepiece of the telescope, and get really quite good quality results. But if you want to go down the route of galaxies and star clusters, unfortunately, you do need to spend a little bit of money to get a telescope with a drive system and a good quality mount and a decent telescope. And, you know, it all starts to get a little bit expensive sometimes, but fortunately, it is becoming cheaper. Now, we talked about the objects that we were going to look at. Let me just show you the pictures. I'm not going to really sort of talk through the details that you can see on the screen. The Tarantula Nebula. This is what the Tarantula Nebula should look like. It was a picture of the nebula, which is in the Large Magellanic Cloud, which we don't get to see from this part of the world. Evidently, we also don't get to see it from Australia when it's cloudy, it seems. But this is what the Tarantula Nebula looks like, and its colour shows us or tells us that the nebula is an emission nebula, and the distinct red colour that you can see is where the energy from the stars, and there are a number of clusters inside this region of nebulosity, of course, nebulosity being Latin, or nebula being Latin for cloud. The star clusters within the center of this gas cloud, the energy from all those stars will shine, and it pours energy, ultraviolet energy, generally onto all of the gas that's surrounding it, and that causes the gas to get excited, and it causes the gas to start glowing in exactly the same way that energy inside your light bulbs, or your neon tubes, will start to glow when the energy from inside, from the electricity, causes the atoms to glow. So it's these gas clouds, the red gas clouds like this one, are where the gas cloud is giving off its own energy. It's not shining by reflected light, but it's giving off its own energy. It's an emission nebula. But that's the Tarantula Nebula in the Large Magellanic Cloud. And as you can see, at a distance of 160,000 light years away. And 160,000 light years, you know, that's quite a distance, but it's nothing compared to some of the objects in the universe. Now, bit of context, the light year is the same as the distance that light can travel in 1 year. Now, light travels 186,000 miles every single second. That's 300,000 kilometers every single second, and traveling that fast, it still takes 160,000 years for the light to get to us from the Tarantula Nebula. And had we been taking a picture of it now through the telescope in Australia, we would have been looking back in time, because the picture we took would have been of the nebula from 160,000 years ago. That's how long it's taken for the light to get to us from there. So it's quite incredible. I've just seen a couple of questions coming in. So a question from that T bloke, asking what sort of size of telescope would be best for beginner on a budget. If you want to get a telescope, certainly for visual work, then binoculars are a really good start, because I've seen a lot of people buy a telescope and then find that actually it's not quite for them, and they go off and do something else and the telescope just sits there. But binoculars can be used for a lot of other things. So certainly start off with a pair of binoculars. But if you are bitten by the bug, which a lot of people are, and I hope you are, then a Dobsonian telescope is a really good telescope to start with. It's called a Dobsonian telescope, and an aperture of about 6 inches or 15 centimeters is a really good size for a beginner. There's a couple of questions I'll come back to in a moment. So we've seen the Tarantula Nebula, so say 160,000 light years away, an emission nebula in the Large Magellanic Cloud. The other objects we were going to look at were the Sculptor Galaxy. Now, we've got a great galaxy in the northern hemisphere that we can see called the Andromeda Galaxy, but this is another stunning example of a spiral galaxy. As you can see, the distance, 11.4 million light years away. So if we'd have been taking a picture of this tonight, and it was second on our list, so we could have taken this as the second object if we had time, at a distance of 11.4 million light years away, we would have taken a picture of that galaxy as it looks 11.4 million years ago, because the light left that would have hit our camera CCD 11.4 million years ago. And I like to think it's quite weird that if an astronomer is sat on a planet around a star in the Sculptor Galaxy, then they would be seeing Earth as it was 11.4 million years ago. And that is really quite crazy. So this is the Sculptor Galaxy. Great way of imagining spiral galaxies, two sort of fried eggs back to back will give you a great idea of what they sort of look like. You've got the bulge in the center, which is the nucleus of the galaxy, and then you've got the, if you like, the white of the egg, which is the spiral arms of the galaxy. But call it starburst galaxy because there's a lot of star forming going on. Stars don't live forever. Stars are formed. Our own star, the sun, formed just under 5 billion years ago, and other stars do appear and get created and then die off. But if you look at sort of zoom in on the sculptural galaxy, you can see all these red blobs. These are gas clouds which are forming brand new stars under the forces of gravitational collapse. So there's a lot of star formation going on this galaxy. And then finally, we were going to look at the 47 Tucanae, a name that really does roll off the tongue, globular cluster. Now, this is an object which looks stunning through a telescope, of course. We've got M13 in the Hercules constellation, which is not quite as good as this. I think the Southern Hemisphere tends to pip us at the post for globular clusters, along with Omega Centauri. The 47 Tucanae is a cluster which is about 13,000 light years away. So it's right on the outskirts of our galaxy. We kind of have this halo of clusters which surround our galaxy, and the 47 Tucanae is one of them. But as you can see, stars of many different colours, and actually I think we should start a campaign here for the Norwich Science Festival. Now if you look, you can see different colours of stars. You can see red stars, you can see yellow stars, and you can see blue stars, and we can tell the colour of stars, we can tell the temperature of stars by looking at their colour. Now what's interesting is that the hotter stars, for example this star in the lower right corner, is the blue star, which is one of the hottest stars in this image, because blue is a really hot temperature. If you imagine a blue poke or piece of metal in a fire or a furnace, then it starts to glow reddy orange before it eventually starts to glow white and then eventually blue. So blue is the hottest color of the stars. And so we can see red stars and yellow stars, which are cooler than this blue star. Now, think about your taps in your bathroom for a moment. What color are they? Run off and have a look if you need to. But the colours of your taps, the hot tap is red, the cold tap is blue. So actually we've got our taps all wrong, because in science, the red things are the cold things and the blue things are the hot things, but our taps are the other way around. So I wonder if we should maybe start a campaign where we swap around those little caps on tops of the taps to make them scientifically accurate. Please don't do that, because we'll have people across the country and county and city maybe who are burning their hands on taps that are coloured wrong. But it's interesting that we associate red with hot and blue with cold, when in reality it's the other way round. So I'll leave you with that thought. I'll just look at a couple of other questions that have come in. So Wendy has asked, what's the best thing to look for and where in tonight's sky if it's clear? Well, it's looking cloudy for me, Wendy. I don't know what it's like where you are at the moment, but we've got the planets on view. So if you look to the west after sunset, I always have to think about that. The direction that the sun goes down in, look over in that direction once the sun's set, because it's dangerous to look at the sun. Look over in that direction once the sun has set, and then just up to the upper left of where the sun went down, you'll see a really bright star. It's the brightest thing in that portion of the sky, and that is Jupiter. Brightest planet or brightest star-like object in the sky at the moment once the sun set is Jupiter. You really cannot miss it. Now, just to the left of Jupiter will be another object which is a little bit fainter, looks a bit sort of pale yellow in colour, and that's Saturn. And you can see that with the naked eye as well. And then look over your left shoulder once you've seen those two, and you'll see a bright red star, and that is the planet Mars, and it looks amazing. Now, a quick pointer while we're on the subject quickly of finding things in the sky. So many of you have got these things called smartphones, and they are fantastic. So this smartphone has got an app, and there are many apps out there. I'm not going to call out any names, but there's free apps, there's apps you can pay for. But what these apps do is, let me just change it. It's currently on the Siding Springs Observatory, which you can't use. Let me just change its location to here, my home in South Norfolk. Where are we? Oh, that's wrong. Hang on. Location, use current location. Done. There we go. So what these things do is, you'll see, I'm actually going to have to skip it on, because if you can see, if I hold it up, I can't see anything on my screen. So you have to, hopefully you can see, that shows the sky as it is now. So it's clearly daytime at the moment. But what it does do, which is really cool, you'll notice that as I move the phone, it shows different things. And that's because the phones have very clever technology in them that know which direction you're pointing them. And what these apps do is they show you what you can see in the sky in that direction. So all you need to do is get one of those apps on your phone, wave it up at the sky, and it shows you what you can see in that part of the sky, and it helps you to find the planets and the constellations and all manner of other things. So it's well worth having a look for some of those apps. Feckless Angels has asked, do you have a favorite nebula to look at? Yes, I do, and it has to be the Orion Nebula. Well, actually, no, do you know what? I'm going to correct that. Actually, not the Orion Nebula. I'm going to say the Ring Nebula. So let me just find it, see if I can find a picture of the Ring Nebula on the internet. So Ring Nebula. Oh, crikey, hang on. Oh, crikey, I can't type. Ring Nebula. Oh, crikey, it's gone bad, isn't it? There we go. Ring Nebula. Here we go. So this is an image of the Ring Nebula popping up, hopefully very soon. What's going on? Oh, there it is. Here's the Ring Nebula. So there it is. That's an image of the Ring Nebula. And doesn't it look incredible? That's how it's good. I must just say, photographs enhance things with more detail. So you will not see this if you look through a telescope. That's actually probably a better, on the right-hand side there, that's probably a much better representation of what it will look like through a telescope. But try and take a photograph of these Ring Nebula and you see things a little bit more like that. And that's because our eyes are less capable of detecting color than a camera is. And you can try it for yourselves, wait until it's dark in, at night time, turn the lights off so it's sort of, you can still see, but there's not any light in the room. And what you'll see is that as you look around, then you can see shapes and forms, but you can't really see color. And that's because our eyes are not as good at detecting color when there's not a lot of light around. So the Ring Nebula, I think, would be my favorite of the nebula that you can see, certainly from this part of the world. Also, favorite galaxy, it's got to be the Whirlpool Galaxy. The Whirlpool Galaxy. It's called M51. Let me just fire up a picture of that as well, so you can all see what that looks like. It's a stunning object where there are two galaxies. It's in Canada's Venatiki, and you can see that there are two galaxies interacting with each other, and they look beautiful. And you can just about kind of see that structure through a telescope. So there's many more questions coming in. My voice is about to pack up, I think. So what I'm going to do, I think, I've shown you how we take pictures, and I've shown you the telescope and how we connect to it and how we use it. So I think we'll perhaps call it a day at that point there. I'll just have one more quick cheeky look to see if that telescope is up and running. I suspect it's probably not. Look at that, still cloudy, and we've still got 17 minutes of our session, but it ain't going to clear up now, I don't think. So thank you all for tuning in. I'm now going to hand back to Natalie. And then there is going to be a YouTube chat. I'm going to jump straight over to there, and I'm going to carry on answering as many questions of yours as I can. And I'm going to preserve my voice because I'm going to be trying to talk for 24 hours in a few days' time. So I'm going to hand over to Natalie now, and thank you all very much for tuning in. I hope that's been of some interest to you.
Brilliant. Thank you, Mark. That was great, especially seeing as you had to change the content there at the last minute. It's really interesting. So huge thanks to you. And as Mark said, he is doing a 24-hour lecture starting at 6 p.m. on Monday. We think he's absolutely crazy. He's trying to blame us that we made him do it, but
it was completely your fault, Natalie. Have I been muted or can you still hear me?
Still hear you?
No,
Yeah.
It's completely your fault, so I hold you completely responsible for it.
God, he's going to be here at the forum, not live. He's going to be doing his event online.
I'm live.
Live, but not live for the audience.
With no audience.
Exactly. So that's going to be 6 p.m. on Monday evening, all the way through to 6 p.m. on Tuesday evening. So the link's on our website if you want to give him some moral support. If there's anyone up in the middle of the night, please do tune in and keep Mark going. We think it's amazing. And
if you don't, I'm just going to go to bed.
He's going to sneakily go off for a sleep. No,
he's not really.
Snooze. And we are raising money during that event for the wonderful charity Barnardo's as well. So huge thanks to Mark for that, and a huge thank you for today. Mark is going to be over on the live chat now for the next few minutes. So please do keep firing your questions, and please keep an eye on the rest of the Norwich Science Festival at home events that we've got going on all the way through to Wednesday this week. We'd love to see as many of you as possible online watching those. That would be great. And also, if you have time, please do take part in our survey. You can be in with a chance of winning a £50 John Lewis voucher or a Raw Dinosaur Adventure Family Pass. So the link should be on your screen now, or you can find that on the Norwich Science Festival website. So huge thanks again, Mark. That was great. And huge thanks to all of you for joining us. We'll see you again soon. Thank you.
Can you all still hear me?